So we begin with the basics. The first construct in logic, it's a statement. A statement is a description of something, any object that we want to describe, or some properties of it, or the object itself. We make a statement, and this is called. So a statement is a description of something. So, for example, I am an instructor for the discrete math course. So it describes the course, it describes the instructor, it describes myself. It's a description of some things, one or more things. That's why we call it a statement. This is a true statement, happens to be true because I am the instructor of a discrete math course. This is a discrete math course, so it's a true statement. I am a student in discrete math. So by this here, by student, I mean a registered student, somebody who has a Zambil record among the registered students. This describes again the course, the students in the course, or myself. It's a description of these things, but it is a false statement, right? It's a valid statement, but its value is false. Here is a statement, I am lying to you. It describes myself, it describes my speech, it describes my statement. Is this a true statement or a false statement? It's a true or false statement? So you think it's both? So
we don't know unless what exactly are you asking?
Okay, so paradox, we don't know, and both. So you're accusing me of lying, possibly. Yes. I have this. अभी मेरे पास है 3 बजे दे देना. Contradiction. Okay. We'll see what is a contradiction, we'll define it, and then we'll give it a precise meaning. Generally speaking, when I ask you questions, almost never would I expect you to say something that we didn't really just speak about. Okay? So contradiction, paradox, these big words, especially I'm really scared of big words. Part of the course learning outcome of this course is that you should not be scared of big words, okay? These are big words with simple meanings, so we'll talk about the meanings. Any other idea? This statement, I am lying to you. It's a true statement, false statement? It's neither. It's incomplete information. That's a good way. It's false. So I'm not lying. Thank you. Yes? What is my previous statement? This is my statement. Anybody else? Say something, yeah.
It can be either of them.
It could be either of them.
So if the statement is true, its value is false, if the value is true, the statement is false.
Do you think it's false or true?
There is like I say, there is a difference between the statement and the value.
Okay, anybody else? Okay, so you want to say something? No. Okay. Let's just see, let's dig deeper into this, so we'll see what is the truth value of this statement. So that's what typically mathematicians do. They want to talk about something, so they want to repeat it again and again, they just give it a name, right? So let's give the statement a name, we call it S, right? So is S true or false? That was the question. So let's say if S is true, right? Just for the sake of assume that for the argument that if it is true, then what does it mean? S is true, this means I am actually lying to you. Yes? If I am lying to you, that's my statement, S is my statement, so S must be false. Make sense? Yes? So if S is true, then S must be false. And if S is false, then S is false, meaning I am not lying to you. That means I am telling the truth. If I am telling the truth, that means S is true and I am actually lying to you, right? So what the moral of the whole story is that we don't call it a proposition yet, this is a statement. We will avoid these type of statements. I don't know if you remember of seeing the Scarface movie. There is this Al Pacino says, I always tell the truth even when I lie. Okay, so we will avoid such statements. This statement is neither true nor false. This is a statement. We never said a statement has to be at least exactly one of them, or at least one of them, or something. So we define a proposition. A proposition is a statement which has exactly one of the two values, either true or false. Not both, not neither of them, not could be, right? This kind of stuff is not going to be allowed. So we are going to talk about propositional logic. We define proposition, and we will restrict ourselves to such statements, right? Let's see if we solved all the problems. Look at this thing. Is this a statement? Please give me a higher grades. Is it a statement? Because why it is not a statement?
It's not describing anything.
Yeah, it's not a description of anything, right? It's not a description. It's begging. Is it a proposition? Because every proposition is a statement, right? With certain additional restriction. So it's not a proposition. So that's why the truth value is a meaningless statement. Okay? Now, by this time, it should be clear why I'm choosing this example and not any other example. So the smart people, because we work in propositions and statements only, so the smart people would say this way. Can I have a higher grade? Is this a statement? It's the same begging, right, on the previous slide. It's not a statement. It's not a proposition. And its truth value is not our job to do this thing. We never talked about the truth value of a non-proposition or a non-statement. Yes, please. Okay, a proposition is a statement. You know a statement, right? A statement is a description of something, of some object. A proposition is those statement, that category of statements which have this additional property of being exactly true or false. Is this clear? The definition of proposition is clear. Good. Okay, so these are not statements. Let's see, 1 plus 1 equals 2. Is this a statement?
Yes.
Why is it a statement? What does it describe? Yes, please. See, speak.
It is describing the addition of two numbers.
It's describing the addition process. Does it describe anything else? It describes equality. It describes the number 2, right? Or the numbers 1 and 1. Or you can say it's a description of something, right? So it is a statement. Is this a proposition?
Yes.
It's a statement which is either true or false, right? And what is its truth value?
True.
Its truth value happens to be true, right? So this is a proposition. Here is another example of a proposition. Is it a statement? 2 plus 2 equals 3? It's again description of the number 3, the equality, or description of the addition of integers, the process of integer additions, right? Is this a proposition?
Yes.
Why is it a proposition? Because it's a statement whose value is either true or false. And what is its truth value? Right? We call it a truth value. The value of true or false. This truth value is false. Okay. Let's see about this. X equals 4. Is this a statement?
Yes.
Again, it describes
Equality.
X or equality or 4, right? Is it a proposition? Is it a proposition? Yes,
It
please.
depends if this is like assignment of a value or if it's
No, equality. It's equality. We always relation. There is no assignment. Okay, assignment that is C++ type thing. No, for that we use gets/gets operator. Yeah.
In this case, x is an unknown thing, so we cannot keep.
So you don't think it's a proposition? It is a proposition. Why is it a proposition? Get?
Because if it's not 4, then it will be something else. It's true or false.
Yeah, it's true or false. Yes, please. G.
If x is equal to 4, then we know that the right hand side is equal to the left hand side, and then it's first classification. So it is a proposition.
But if x is 19? Yes. So yes, please. Yeah, it's not a proposition. Its truth value depends upon the value of x, right? So the x I have in my pocket, which happens to be equal to 4, then we'll say it's true. So for your x it is true, for my x it isn't true, or something like that. This is not really, don't bother too much, because in like 1 hour we will expand our language to be able to talk about this, right? So we will make these propositions with these are actually called predicates, okay? So, but these are statements, it's the description of the x or the equality, and these are not really proposition as such as our current knowledge is. So that's why its truth value is the meaningless question, okay? Okay. So generally speaking, questions, begging, commands, suggestion, opinions are not propositions, okay? We will restrict ourselves for today and for the rest of our lives to propositions and predicates only, okay? We will talk about statements that are either true or false, not both, not neither of them, right? Not it depends, right? Now, it doesn't mean that we will know always that this is true, this is false. That's a different story, is going to come in a minute. But the reason I introduced this x equals 4 is to be able to talk about this stuff. Now, these statements are, strictly speaking, in our terminology, not really propositions, right? But everyone knows the Pythagoras theorem, right? What does the Pythagoras theorem says? Well, there is a trigonometry version of it, but let's talk about just basic number theory version of it. It says that a squared plus b squared equals c squared this equation has a solutions where a, b, c, all three are integers. Okay, so this I try to make it more like a propositions, even though this a is a variable, b is a variable. This a little bit meta proposition is talking about values of these a, b, c. So, but that will be clear in a minute. I want to make this point that to find out the truth value of propositions or statements, I use purposefully the word statements here. Truth value of statements is not necessarily easy to find. Okay, is this a true statement or false? Why do you think it is true? Those of you who think it is true, why do you think? Yes, please. Okay, so let's it has not been proven scientifically. Nothing gets proven scientifically. Proof is mathematical thing. It has been observed in many different places, but right now we have to analyze this linguistically, okay, in terms of language. Yes, please.
I think it's false.
Okay, you think it is false. Why?
This theorem only works for the sides of a right angle triangle.
Yes.
Here it's written A, B, C are positive integers. If I just plug in the equation, it's not very
Yeah, but it says it has solution. It has some solution. So again, this will become clear tomorrow in the next session. But it's
there exists three possible
now,
numbers which satisfy.
so just a second. You made up a whole story which is correct, but right now we are talking about just the statement on the face value, right? Right angle and trigonometry, these are exactly the same statements, but even there, if you really think about it, the statement is okay. So sorry, you were saying
It said that it has solutions. Which
it
means
has
that
solutions.
any possible value of a, b, and c. So my mind naturally went to 3, 4, and 5.
Okay.
And I was like, okay, that's the solution.
So he thinks because the statement says that this equation has solution, and that is a true thing because it has solution. A equals 3, b equals 4, and c equals 5 is actually a solution. A is integer, 3 is integer, 4 is integer, 5 is integer, right? So if I plug in here 3 squared plus 4 squared, which is whatever, that's equal to 5 squared, 25, right? 3 squared plus 4 squared is 9 plus 16, that's equal to 25, yeah? Equal to 5 squared. So I hate these. Okay, so 3 squared plus 4 squared equals 5 squared. The statement says, I know some integers which when I add them in this fashion, it will equal to the squares of 2 of them will add up to the square of the third one. And that's just true. 3 plus squared plus 4 squared is equal to 5 squared. So this is a true statement. Is this clear? The statement says there are solution, there is a solution, at least one solution to this equation, and there is one solution. There may be many more. Make sense? Integers? Yes, please.
Sir, do we know, are we talking about the theorem right now, or are we just talking about the equation?
So the theorem actually makes this equation, right?
So basically, can we just say that for any arbitrary integers a and b will always result in an arbitrary value of c, if that's right, it's true?
Okay, so let's say if I make a statement like this, that there is someone in the class who is GPA 3.7643. Is that a true statement? Depends on what?
If you analyze the class, if it's
Yeah.
turns out to be true.
If there indeed is a person whose GPA is exactly 3.7624 or whatever I said, then my statement will be true. And if none of them, if all 120 of them, you or whatever, however many you are, if all of them have GPA either above 3.7623 or below 3.7623, then my statement is false, right? Here Pythagoras made a statement that there are some three numbers who, when I add the square of 2, then I get the square of the third one, right? And they are integers. And that is a true statement because at least we know a squared plus a equals 3, b equals 4, and c equals 5 works for this. So it's a true statement in that sense. Again, don't worry too much about it. This is going to be, this is what's our predicate and quantifier statement, which is coming in a while. Yes, please.
So when we're talking about statement, we only focus on the formula. But if like we say that the statement is a squared plus b squared has solution with a, b, and c, then we can find like more.
Yeah. Yes, you are right. Exactly. That was the thing, that you don't focus on just this a squared plus b squared equals c squared. It's a whole sentence. The sentence says this equation has solutions, right? If you look at it as a whole, then you see that that's actually a true statement. Okay? Is this clear? How long ago is this thing? 500 BC? Okay. Now, this is the note, it should have come earlier, that strictly speaking is not proposition. That's why a lot of confusion at this stage, but I want to make a point here. In the next examples will make it clear what do I want to say. Finding the truth value of propositions is not necessarily an easy thing. That's what I wanted to say. So this is what we know. But the reason I introduced that because I wanted to talk about this, the Fermat's last theorem. Fermat wrote it somewhere that a cubed plus b cubed is equal to c cubed has no solutions among the integers. So if you just replace the 2 with the 3 in the Pythagoras equation, then this statement is not true. Okay? So Fermat said a little bit more. It's just said not just 3, 4, 5, 6, any integer. For any integer bigger than 2, a to the n plus b to the n is not equal to c to the n for any combination of a, b, c. Okay? So he wrote this statement in 1637 somewhere in a notebook, and he said that I have a very short proof of this statement, right? It turned out nobody knew the proof, and people have been trying about this, that is it actually true or not. It took about 350 years for Andrew Wiles to prove that this statement actually is true. The truth value of the statement by Fermat is established 350 years later, more or less. Okay, Andrew Wiles, x to the n, y to the n equals z to the n has no solutions among integers. That is actually the theorem. It took him 7 years to prove. A lot of things. It's a big story. A lot of people have been working on it. And he published a paper on this in 1993. Then somebody found a flaw in that, and then in 1994 he fixed the flaw. And a Stanford number theorist, not Stanford, Princeton. Okay, is the point clear? Finding the truth value of statement may take a lot of time. Okay. Here is another one. It's the Euler's conjecture. In the spirit of Pythagoras statement and the Fermat's last theorem statement, Euler conjectured that, okay, let's involve 4 integers, a, b, c, d, right? So Euler conjectured that a to the 4 plus b to the 4 plus c to the 4 is not is equal to d to the 4 have no solutions among integers. Just like Fermat said, for 3 integers, any power. Euler's statement is also about, it's a more general statement. This is one special case of that, right? So 1769, Euler conjectured that this has no solution. 250 years later, 220 years later, many other solutions for this particular case, a to the 4, b to the 4, Norm A. Elkis found this counter example, said no, actually if I plug in a to be this number, and b this number, and c and d, then actually it satisfies this equation, right? So for this a, b, c, if I add their fourth power, I get the fourth power of d. Does it make sense? Found the truth value of a statement in 220 years or something, right? Roughly. A lot of time. Yes, please.
So I'm just trying to understand the words. Are we just trying to analyze the previously mathematically proved solutions, or are we just trying to analyze whether this can be true or false?
No, we are just talking about it. So here is a statement, either true or false. I'm saying it's not easy to find truth value. We are not going to talk about Euler conjecture. We are not going to talk about Fermat's last theorem or the Pythagoras theorem. We may mention all of them. Fermat's little theorem is going to come in number theory. Euler conjecture, no, some other Euler formula is going to come in graphs, but this we're not talking about the math of it and how to prove it or how to disprove it or how to find these numbers. I'm just saying, here is a number. If I pose this question to you, that is it true or false, and you couldn't find an answer, you should actually maybe think that maybe it's a very hard question.
So if there is an equation based on a theorem, so could we say if it's true because it's still a theorem in some sense?
No, theorem is a true statement, right? So far I only wrote Pythagoras theorem because we know it is true. I wrote Fermat's last theorem because now we know it is true. People always thought it was true, but we only found out exactly like this 30 years ago, right? And I never said Euler's theorem. This theorem is Euler conjecture that is proven to be false. It is not a theorem. Okay? Here is another one, the Goldbach conjecture. Again, been open for close to 300 years. Very simple statement. It says if you take any even integer, you can write it as the sum of two prime numbers, right? All of you would know the prime factorization theorem. You can take any number and write it as a product of primes. But can you write it as a sum of primes also, sum of two primes? Okay. So here is the illustration of that from Wikipedia. These are even numbers. I'm going to show you. So I take prime numbers and then intersect with the same another prime number, the blue prime number and green prime number. At the intersection, I'll see which odd number which even number appears funny. Okay, so let's just do this. Can you write 4 as a sum of two prime numbers? Can you write 6? Give me sums. Can you write 6 as sum of two primes? 1 plus 1 is not a prime. 3 plus 3. 8. Can you write 8 as a sum of primes? 3 plus 5. 10. 7 plus 3 or 5 plus 5. 12. 7 plus 5. 14. 11 plus 3 or 7 plus 7. What is the next one? 16. Even numbers. Can you write 16 as a sum of two primes? 11 plus 5. Can you write 18 as a sum of two primes? 13 and 5. So look at 18 here. You can get it from 7 plus 11 or 13 plus 5 and maybe other ways too, right? Similarly, you try every number, every even integers that you can get the help of any computational power you can think of. Any number people tried, they found it to be actually you can write it as a sum of two integers, sum of two primes. But is the statement true? We don't know, right? It's still an open conjecture. People tried a lot, couldn't find anything. Now you can come up with one even numbers, let's say 122, and tell me that no, I tried all possible prime numbers, the pairs of prime numbers, or some other way convince me that it cannot be written as a sum of two primes, then it will disprove the conjecture. Just like the Euler's conjecture was disproved, it could be disproved by just coming up with one counterexample. Okay? So this I will leave it as your homework. Work on it and see how do you make it. There's a lot more. Sorry?
Why don't you tell us to solve the even hypothesis for the
You have to begin with this first. This is good because this is I have more slides about it. So we talked about propositions and their truth values and see how do you find it and what is the statement and other stuff. The reason I told you Goldbach Conjecture, I left it as a homework because I'm going to build upon it here. So a proposition is a statement which is either true or false, right? We generally don't associate too much to it, right? We have no emotional attachment to this stuff. For us, these are just variables and they're either true or false, right? Sometimes we may not know whether they are true or false, right? But they will have only one value. We don't know is a different story, okay? So for us, these are called the Boolean variables. Most of those of you are familiar with programming. The bool variable is just a variable which takes a value true or false, right? We'll denote them by P, Q, R, S, A, B, C, right? Now, if I restrict myself or my language only to propositions, it's very little I can express, right? Remember, I couldn't even talk, I couldn't express in terms of proposition the Pythagoras Theorem. I had to just borrow stuff that from next week and say that, okay, let's assume this is a statement, and very little can be expressed if you are allowed to just make such small statements, right? So in English also, we have small phrases, small sentences, and then we combine them using to make compound bigger sentences to express much more, right? We use this not, and, or, if, then, mostly many different combining words that combine two sentences and stuff. So we'll do exactly the same thing, except for we will give them very, very precise meaning, okay? We are working with a formal language. We'll not make any nonsense stuff like English do. I just generally get very extremely surprised. How can people communicate in any natural language, English, Urdu, Pashto, right? It's a lot of context. Look at this statement. I'm saying your faculty advisor tells you, you may register for CS210 or CS212. What's the meaning of this?
You could register for only one.
Well, who said that? Why can't we register for both? Yes.
Mathematically speaking, it means you can choose
There is no mathematical, it's English. This is the English or.
English either one or the other.
One or the other? You can't do for both? If you, yes.
Since it
So
is-
if somebody tells you you can choose this one as an elective or that one as an elective, that means you cannot do both.
So that's the convention of speaking, and that's what we use.
So there is a lot of context, a lot of other stuff, okay? Here's the thing, every student gets a grade, right? It's a true statement, every student gets a grade. Does it mean that there is a grade that every student gets? What would that mean? If we take that meaning, there is a grade which every student gets. That would mean everybody gets F, right? Or whatever, C or D or whatever you like. Yes? So, does every student get the same grade? So know what? Know what? This is a true statement, right? You must have heard everywhere. It's a common sense thing. Every student gets a grade. So does every student get the same grade? No, meaning what? Students get different grades, right? So does every student gets different grade?
because some students get similar grades.
Some gets,
So that's not different then.
They all will get unique grades.
Yeah, so that's the problem with these languages, right? That's why I ask you to stop talking in that language and start more precise language. This is what, because someone like me who take languages seriously, this is what I do with my wife. So Why did you buy 12 gallons of milk? Well, because you said to buy a gallon of milk. And if the store has eggs, buy a dozen. Right? So if the store has egg, I got a dozen milk, a dozen gallons of milk. Right? Nothing wrong with it. Totally correct. And it's really surprising how we make actually. That's the human intelligence actually. We have a lot of context, a lot of background, a lot of subtext, a lot of so we associate, we interpret stuff very differently. So that's why when we make combined sentences, like this is the or thing, too many questions. This is also students in a grade, two things. When we do this combination, we will give them precise meaning. Okay. So that's why we'll not talk too much, because that just makes things confusing. You make up a story of your own. I will describe these things, the next few slides, just like this. If I have a proposition P, I can make a new proposition out of it. I will call it not P, or the negation of P, and its truth value is given as follows. Right? This truth table, this is called a truth table. It says if P is true, this is all possible values of P in the first column, all possible values of not P, negation of P, right, in the second column. So when P is true, not P is false. When P is false, not P is true. It's clear? That's not P. You make up whatever you want out of it. I'm going to give you one interpretation the way it's a correct one, but that becomes confusing at points. This is just more precise, right? Those of you who work with Java, C++, C, this is how we write it there in conditions, the not P. In LaTeX, we write this way. This is the general mathematical way. It's written as /neg, slash for negation. That's a symbol, and we'll give you this symbol. It's pronounced as not P. In some old British mathematical convention, they write it as P, and top of it is a bar, over bar on that, right? It's not correct because it's used generally in set theory nowadays. When P is true, not P is false, and vice versa. That's how. How many of you get this joke? How many of you have seen this joke? Not false is funny because it is true, right? That's a C, not false, right? Negation of false. Okay. Here is the thing. Today is Friday. If I want to say today is not Friday, I will just say not P, right? It's not the case today is Friday and today is any other day. Now, very good to, easy to translate. If you ask a second grader, negate today is Friday, they will say, no, today is Wednesday. But that's not the negation, right? Why is today is Wednesday not the negation of this P? Just please think about it, pay attention to this thing, all of you. Why is today is Wednesday not the negation of this statement P? Yes, please. Yes. Yeah, maybe you're right, but a little bit too vague. You made me even more confused.
If you reverse that statement, you will find that today is done. It does not match it.
Okay, some made some sense, but I will come to you in a minute. Yes, please. That's a good idea.
If you say today is not Friday, it could either be Monday, Tuesday, Wednesday, or any other day. But if you say today is Wednesday, it only classifies as Wednesday.
What's wrong with this? If I say today is Wednesday, can today be Friday then? Cannot be. So what's wrong with that? Why it's not the negation?
Monday or Tuesday, but it's not the case. If you were to say today is not Friday, it could be Monday or Tuesday. That's it.
Okay, so you're right, but I want you to say something. You have to understand to listen to what I mean, okay? Not listen to what I say. You should not listen to what I say. Only listen to what I want to say, okay? And that you interpret from what I do say. Yes?
If we consider these two sets, that today is Friday, and if we consider that its negation is today is Wednesday, then the set that today is Wednesday and that today is Friday, it does not combine together to form the whole.
Okay, yes, that's good, but don't use the word set theory. Here is you also gave some good answer or some good direction, please.
For example, if our state was today is not Friday, then going like negating that would be difficult.
So I made it simple. No, I negated it. You have to find problem in it. So maybe what you wanted to say is what I wanted to hear. So let me just tell you what you think. Three of you gave roughly the same correct answer. But I told you, pay attention to this. There is a reason I didn't actually talk about this too many things, the set version of it, the other versions of it, right? Monday, Wednesday type stuff. I said P and not P have to have this property. If one is true, the other must be false. If P is true, not P must be false. If P is false, not P must be true. That's it. Now let's assume let's say we start to live in a world where today is Friday, and I said not P, today is Wednesday. Okay, that's a statement. We don't know which one is true, which one is false. Now let's say I make the statement on Tuesday. What is the value of P on Tuesday? What is the value of today is Friday on Tuesday? It's a false statement. What's the value of today is Wednesday on Tuesday? Both are false. That's why it cannot be the negation of them. A negation, if one is false, the other must be true, right? And now you do this kind of analysis on any day you want, right? Monday, Tuesday, Wednesday, Friday, whichever day. I make a statement, today is Friday, and I make another statement, today is not Friday, or it is not the case that today is Friday, right? Or whatever you want to make it. Now think of these two statements. Try to see the truth value of these two statements from the Mars, from the moon, from on Monday, on Tuesday, in the morning, in the evening, whatever you say. If one is true, the other must be false, right? And their values must always be opposite of each other. Okay, the truth values. Is this clear to everyone? I'm sorry I couldn't hear completely to some of your answers. You're sitting far away, but I assumed you were going in the right direction, but this was the clearest way to that how you should have answered. Okay, it's clear? Yep. Okay, 2 plus 2 equals 4. What's the negation of that? 2 plus 2 equals 5, right? 2 plus 2 is greater than 4. No? Why is 2 plus 2 greater than 4? Not the negation. Again, by the same reason, right? If I write 2 plus 2 equals 5, the negation 2 plus 2 greater than 5, the supposed negation 2 plus 2 greater than 5 will be both simultaneously false, right? Now, combining more than one proposition, there was just this called the unary modification. Now we are going to do binary, working with 2 or more propositions, right? So 2 to begin with, and then we'll make further compound propositions. Combining 2 propositions with the AND, right? So if I have 2 propositions P and Q, I can make another proposition P and Q, whose truth value is given as follows, right? It's denoted by P and Q. This symbol you get in LaTeX by /wedge, /wedge. This will give you, so P and Q is a proposition whose truth value is given in this table, right? Can you summarize this truth table easily? So that I know exactly when is P and Q false and when is it true? Yes, please. Yeah, okay. So a little bit more precise, you're correct, but both what? Can you guys say something about this thing? Can you summarize in your words this truth table? Yes, say something. What does both? Okay, if both P and Q are true, if P is true and Q is true, then P and Q is true, and otherwise it is false, right? For all other cases it's false. Yes, please.
If at least one proposition is false, then P and Q will be false.
Yeah, okay. Same thing. Okay. So is this clear? If you want to have, we must have seen this type of circuits, right? When will this bulb be on? When both X is true passing current through that and Y is current through passing current. So this is how it's denoted. Sometime in C++ type stuff is P, this double ampersand sign. It's written as P and Q, is pronounced as P and Q. and P and Q is true when both P and Q are true. Okay, otherwise false. Again, today is Friday. Today it's warm. Today you can do what is P and Q? Not the value. What is the statement? Not its truth value. Just make the sentence first. It's a warm Friday today. Today is a warm Friday. Yes. Yeah, today is Friday and it's a warm day. Yes. Anybody else?
I have a question regarding the previous slide.
Okay, good.
So, sir, the proposition P and Q, if we're talking about its negation, it will be true in all cases where P and Q is false.
You want to talk about the negation of what? The negation of P and Q? Okay, we'll come to that. So we are just building up, right? So you're taking the previous modification process and this process together. We'll come to it in a minute, so let's go systematically, okay? Good question though. We just learned one thing and we learned another thing. We have to be able to apply them to each other, right? And we will do it. Okay, if I don't, then please remind me if you didn't see exactly what I said. Your answer to your question. So it's a warm Friday, right? Now, if you make this statement in a December 27th Friday, will it be false or true? Right? It will be correct translation. It will be false, right? Because it's not warm on December 27th, most probably in this place. If you make this statement on June 22nd Thursday, what will happen? It's false. What if you make this statement in a December 22nd Saturday? Still false, right? Both are true, both are false, and so that's how you should know. 2 plus 2 equals 4, P and Q is 2 plus 2 equals 4, and 5 is greater than 1. So I just want you to know that now we are learning to make bigger, more complex statements in the language, right? And we'll build upon this to make up, build the whole computational mathematics building, okay? Or again, when we have two proposition P and Q, P or Q, P slash VQ is written, its truth value is another proposition whose truth value is given by this truth table, right? Again, any summary of this table? Can you summarize this truth table? Someone from 1, 2, 3, 4. Fourth row? No? Yes, please.
Only false when both P and Q are false.
It's false when P and Q are false, and only false, yeah.
So P or Q is true when either P is true or Q is true.
Sorry, say it again.
P or Q is true when either P is true or Q is true.
Okay, either P is true or Q is true. Again, it's a little bit of this English or, right? The second, when you use the word or, you use the word. So you use the English type of or, right? So or both, and you have to add or both. Either P is true or Q is true or both are true, then P or Q is true. But another way to describe it is it's only false when both are false, otherwise true, right? So that's the easier way to do it. Talk about the false rows. Here is the circuit description of this thing. In C++, it's written with a double pipe symbol. And it's true when one or both of P and Q are true, otherwise it is false. Okay, again, this you can do this thing. Now when I make this statement P or Q, what is the statement P or Q? Yeah, you may register for CS210 or CS212, exactly the same statement as we made in English. But now can I ask you, can you register for both? It's immediately clear, yes, you can register for both, right? So that's the beauty of our language. We'll just learn more stuff like this when we want to exclude what to do. Okay, so one more thing, XOR, exclusive OR, P, if P and Q are true proposition, P exclusive OR Q is written as P, this is called O plus, slash O plus. This P XOR Q value, its truth value is given by this truth table. Okay. Any summarization of this truth table? Someone from this place? No, just people under the camera. Just say something. Can you summarize this truth table?
So if either both of them are true, either both of them are false, then it's false.
Okay.
Otherwise it's true.
Okay, good, good. Not summarized enough, but correct. Yes.
Either P is true or Q is true.
So P or Q is true with either P is true or Q is true, but not both. Right? But not both. Yes, please.
It is only true when only one of the.
Yes, that's a easier, better way of describing it, summarizing it. Yes, please.
It's only true when both have the same truth value.
When both have different truth value. Yes, good attempt. That's a good observation. Yes, please.
It'll only be true if they have different truth values.
If they have different values, if P and Q have different truth values, then P is exclusive or Q will be true. Yes, please.
What if there are three statements?
Yeah, so we'll come to that again. That we'll expand it further. Right now we started with 1, then 2, then 3 and more, and we'll just do that. Okay, but it's a good way to do this. So in English we will say P and Q, P exclusive or Q is true when exactly one of P and Q are true, right? In the previous one, when at least one of P and Q are true for or, and it's exactly true, both of them are true, then it's true. So, and this is actually, by the way, it's called in circuitry, it's called the dissimilarity gate, right? In digital electronics, this is an inequality or dissimilarity gate. Unlike the next one, its exclusive or is written as O plus when exactly one of them is true. In English, you would say this, how would you say this P exclusive or Q? How would you say P exclusive or Q for this P and this Q? One of you here. This side is very silent. Please say something, okay? No? Yes, please, go ahead. So you cannot register for Anthropology 101? You use the only a little too early. It's too preemptively. Can you say it again, please? And no, it's yes. You want to say? No? Yes, please.
You may register for CS210 or CS212, but not both.
Yes. So that's what you needed to add. Otherwise, it will become exactly what the previous issue was there with the English statement. Yes.
Should the first one itself shouldn't it be must? Shouldn't it not be must? Because when option letter there, you don't register for either.
Yeah. So. Well, that's a really good way to do this. Yeah, it's a very good thing because all the other translation, even what I was thinking was also this thing, that if I say this thing, this you may register for CS210 or CS212, but not both, that kind of allows the possibility of somebody not registering for either of them, right? So you have to be tactical in making the statement so you don't make this room for this. I don't know how did. Okay. So yes, in this statement, if you stretch it, you can see this thing that if you don't register for either of them, you can actually still survive. But that's not what is meant by or, exclusive or. Very good point. Yeah, I will come back to you. Yeah, that we needed to do something, right? So it is easy. Again, that's the problem with English and our capabilities in English and other stuff in the context. If I say you must register for exactly one of these two courses, this will be the obviously exactly correct thing. You must register for exactly one of these two courses. Yes, that's what we meant to say, but you have to be careful. You will get a lot of exercises for English to math translation and math to English translation, and you have to be careful for those things. Yes, you wanted to say something? Okay. So, but good point. Well, we will not talk too much about math, English anyway. If then, this is really going to be our next whole session is going to be about this, if then. One way to combine, another way to combine two proposition P and Q is by making the statement if P then Q, right? And it's written as P implies Q or P slash right arrow Q. Its truth value is given as follows, right? So we will talk about this truth table in detail. Right now, I just go in the same manner and ask you to summarize it. Can you summarize this truth table? Somebody? Yes.
It's only false when Q is false, otherwise it's true.
When Q is false, this is true. But good attempt. That's what.
When P is true and Q is false, only then is P then Q.
Anyone else? Can you summarize this thing? P implies Q. Yes, please. We pronounce it as P implies Q. Okay. Yes. If P is true and Q is false, then P implies Q is false. Otherwise, it is true. That's what we mean by saying it's false. Anyone else? Okay. So this we'll talk about is called the conditional statement. All exactly what the if construct works in programming languages. P implies Q is false when P is true and Q is false, right? When the condition is met, there are special words to this thing. Let's come to this. That's why I introduced the Goldbach conjecture. There are too many other conjectures. Here is statement P if you solve the Goldbach conjecture. And statement Q is that you got an A in this course. You will get an A of this course or whatever. Your grade in this course is A. Can you combine them with the implication with if P then Q? What will be if P then Q? Yes.
If you solve the Goldbach conjecture, then you get an A.
Then you will get an A in the course. Anybody else? That's his standing. Yes.
So the first one is also true, the second one also true. So it will be true.
No. I just make the statement. Just make the state the fact.
The Goldbach conjecture,
Then you will get an A, right? So it's a policy, promise, conditional statement, right? And that's it's a standing policy in the class, okay? It's my promise. If you solve the Goldbach conjecture, you will get an A in this course, okay? We'll talk about this in a while. P is the statement X is divisible by 4. Again, not exactly proposition, but let's see. And Q is the statement X is even, right? What is, can you combine them in implication? Can you make a compound proposition in the implication of 1 and 2, P and Q? Yes. Can you please somebody here, this place? Yes. Can you say something? Yes, talk to me. Sorry, please say it again. No, no. If will come for. So, what is the condition and what is the conclusion? If X is divisible by 4, then X is an even number. Yes. Yeah, but that's again. So, but I wrote the way we write it is just to not confuse ourselves. It will be clear why I'm insisting on just saying. Always make the statement just to keep you clear and not to avoid making mistakes. If then, right? So if the condition, then this is the first time when these are not like P and Q is the same as Q and P. Here it's not, and we'll talk about that in a minute. You don't understand the third row? Well, it's not really much there to understand. Okay? This is how we define our language. This is the meaning of stuff, right? You may say that you're not, some people do think, and that's why I have a whole next set of slides is about this thing, explaining every single row of that, right? So please hold on to your thought. We'll come back. I have one more thing to do, one more connections, one more compounding way, and then we'll go discuss a little bit more and then come back to your questions, okay? Okay, so if and only if, and hopefully this type of things will also make bring some clarity. If P and Q are two propositions, then I can combine them with the if and only if, P by implication if, bidirectional implication, P slash left right arrow, its truth table is given as follows, right? P if and only if Q is true for this possible some values of P and Q, and for this is false for other values of Q. Anybody who wants to summarize this thing here, please. This anybody who is sleeping, please. No, you're not sleeping, or no, don't want to summarize, or what do you want to say? Huh? Both? Both meaning what? Not sleeping. One thing, please just make it clear. I am very bad at this, my communication skills, and especially my Urdu and this contextual thing. When you say this, what does it mean? Means yes, right? Yes? So I asked you to answer the question and you said no. You said no and you nodded your head like this. Okay. Anyway, yes, you want to say something?
I want to ask that isn't this truth table a negation of the exclusive or?
Oh, good. So she said, "This isn't this truth table the negation of exclusive OR?" Yes, please.
Like to describe the table.
Yeah. So you describe and summarize the table. We'll come to that.
When the truth values are the same, then it is the same.
Okay. So his description or summarization is if the truth value of the atomic propositions P and Q are the same, then the P if and only if Q is true, otherwise it is false, right? You know, if you recall about exclusive OR, as she observed, they said that P XOR Q is true if the truth value of the atomic propositions are different or unequal, right? So in that sense, yes, this is the negation or the opposite of that. That's why this is called the similarity gate or the equality gate. If you want to check the equality of P and Q, you use the if and only if gate or construct. Even though all of these are derived, okay, the only basics are and, or, and not. The rest all stuff can be derived, can be expressed in a slightly elaborate way of and combinations of and, or, and not. Okay, so this is what say P if and only if Q is true when P is equal to Q. Okay, the truth value of P. Now, previously we made a statement. Can you repeat that? Let's just go here. This P implies Q. If you solve the Goldbach conjecture, then you will get an A in this course, right? Now I'm making the statement that you will get an A in this course if and only if you solve the Goldbach conjecture. What is the difference between these two policies? Please pay attention to this. Do you guys see difference between these two policies? You don't? Who doesn't see difference in these two policies? The previous one says you will get an A if you solve the Goldbach conjecture. This one says you will get an A if and only if you solve the Goldbach conjecture. Do you see the differences or no? You don't see difference? You see anybody who's not convinced that these are two different things? It's okay, you can say it. We don't know yet, right? We'll find out. You don't think there is any difference?
I think I can't really compare them both. Can you please explain why they are different?
Okay, good. Those of you who do see difference there, can you please very short, easy description so it's clear to them, to her, to this thing? Yes.
There's two things that firstly it says that you cannot get an A without solving the conjecture, and secondly it's a true implication that says that if you got an A it means that you have solved.
Okay. Anybody else, please? Yes, you.
So in the first
Let's see. He hasn't spoken yet. So
in the first one, the initial one, there is an added benefit to solving the Goldbach conjecture, as in you can get an A if you solve the Goldbach conjecture, while there's still being a possibility of you getting an A on your own by going through the course. But in the second one, you cannot get an A in any other way apart from solving.
good. Yes. Okay, so let me just repeat her answer to you. So, and then if you still have question. So she says the second one, this one says the only way to get an A in this course is solving the Goldbach conjecture. While in the previous one way to get an A is Goldbach conjecture, other way is to solve the Alzhar conjecture, another way is to just get 100% on your final exam, or just do whatever you want. There are many other ways to do it, right? Getting a good grade by intimidation, getting a good grade by threatening, by begging, by bribing, many other ways. Yes? Is this clear to you? Just a second. Is this clear to you now? If and only if has a different meaning than if, right?
Sir,
Yeah.
but this statement also implies that if I get an A in this course, I will automatically solve the problem.
You must have solved the Goldbach conjecture. That's what this says, yes. It's a bidirectional if. If you get an A, you would have solved the Goldbach conjecture. If you solve the Goldbach conjecture, you will get an A. In the previous one, if you get an A, doesn't necessarily mean you solve the Goldbach conjecture. You may have just solved some other big statement, the theorem, right? Is this clear? One of my instructor would used to put it like this, and these days it may make more sense to some of you. He would also say, when I say if X is a general, then X is an idiot, it does not mean that all idiots are generals, right? It only means all generals are idiots, right? That's what it means. So don't never ever confuse it. It's an extremely important concept, an extremely important thing, and people are very prone to make an error here. I remember, so let me just tell you, because it's time for a break, and so I was going to Dartmouth and that instructor who wrote me a recommendation letter, and then I later found out that he wrote in the recommendation letter that Imdad doesn't make the mistakes of if P then Q, P implies Q. He doesn't confuse P implies Q with Q implies P. It's such an important thing. He gave me a recommendation for a master's program, and so it must say me, at least in his view, and I would be very proud if I can say about someone that he never makes this mistakes, or she never confuses P implies Q with P implies Q. It is an important thing, okay? Pay attention to this. Okay, so I will take a break after finishing these slides, because now it's very few things left, and then we'll come back to this exactly the implication, and I have one question in waiting already about that things. So this was earlier a question, what if there were 3 propositions, right? You asked a question, right? So 3 or more propositions. So if you have a compound proposition made up of many atomic propositions combined using and, or, not, and something, what is its truth value? You want to find out its truth value. Obviously, its truth value will depend on the truth value of this constituent atomic propositions. So we will make a truth table which tells us the truth values of the compound proposition, or different possibilities of truth values of compound propositions. So how many atomic propositions are there in this truth table? In this compound proposition? 2, right? P and Q. But it's combined through more than one. It's not a binary process there, right? It's more than that. Can you pronounce this statement? Yes, you. Can you pronounce this statement? Yes, yeah, go ahead, Chavez. It's not a sin if I ask, even if I'm not pointing to you, you can answer. Yes?
Not Q or not and.
Not Q or?
Not and Q.
Not what?
Is it and?
This is and, this is or. Can you say the whole statement?
Not Q or not and Q.
Not or. Where is not or?
Not P and Q.
Yeah, not P or and Q. Yes, please.
Not Q or not P and Q.
Yeah, not Q or not P and Q. The brackets you have to say some one way or the other, okay? But you have to pay attention. There is a meaning to this thing. This whole compound proposition is ORed with, when it's compound proposition, whatever proposition, it's a proposition. Its value will be either true or false, right? So that value will be ORed with not Q, Okay, the compound value of the compound proposition. The way you make its truth table, you have to find out what will be its truth value depending on P and Q, of course. You make a column. Yes? Yes, please a little bit reduce the talking, okay? These guys are recording, and so let's blame them for not making requiring you. So you make a column, you collect all possible values of the atomic propositions. We'll talk about this, how many will be there. P and Q, possible values are 2 to the 2, right? 2 times 2. 2 values for P, 2 values for Q, for both 2 values is 2 times 2, right? So, and then when I know the value of Q, I know exactly what would be the value of not Q, right? So, what will be the value of not Q when Q is true? False. What will be the value when Q is false? Oh, that's not P. Okay. So, true, then this will be false. When P is false, then true. This, you see how you make it? Then next we will make the truth value of not P and Q. Where is not P? This proposition, and we'll AND it with this propositions, right? So, when I AND a false with a true, what do I get? False. And a false with a false, a true with a true, and a true with a false, that's a false. So, I will get, so it's not Q because I'm going to need it later. So, but now it will hopefully come, yes, not P or and Q. This will be that false, false, true, false, right? True, true, false. Yes? And now I will take this not P or Q and OR it with this not Q, right? What will I get? Somebody please dictate to me the whole column. That's a good thing. Q Malikar column में क्या किया? True, false, Q किया? Okay, good. That's a very good question, right? There is no rule, no requirement for that thing. What are the possible values of P and Q combined? What are the possible values of P and Q? Please tell me. Okay, so how many possible combinations are there? 4, right? Yes. So there are 4 possible. Have I written all 4 here? Right? Generally speaking, if you want to make a truth table of this, systematically write from the first side, true, false, alternate it. Next one, 2 trues, 2 false, alternate pairs of trues and pairs of false. Next one, 4 trues, 4 false, right? If there are 3, then there will be 8 rows, 8 possible combinations, and you will get all of them, right? Think of it as generating, you know how to do it, no? You know programming? You know computer programming? Thodi si. What do you mean thodi si? So, you know what does this mean? P in true or false, right? So, P is equal to true and or false or whatever. Some one way or the other you can implement it in Python or C or Java, right? This is a for loop. For P gets the value true and false, right? And then write for Q in true false, right? Can you read this? Then write another nested loop for R in true false. If you run this thing and you just write print whatever C out or system.out, P concatenated with Q concatenated with R, right? You will get exactly the way I told you. R will be true, false, true, false, true, false, true, false. Q will be true, true, false, false, true, true, false, false, and P will be true, 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 false, 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 false. Yes. That's how nesting works, okay? So if you do it systematically, I always do it this way, then this way I don't miss any combination. Yes? There will be 8 rows. If there are 3 atomic propositions, it will be 2 raised to the power the number of atomic propositions. Yes, when we do counting, these things will come. It will come before that also. Okay, please.
Can you just explain that notation again?
No, there is their notation. So generally we say this thing. So you guys are used to this notation for EPS. For I equals 1 to 10. What is this? You know this notation too, right? What does it mean? Oh, you write it like this. This is exactly that thing, right? If I was this in this language, if I was writing this thing, I'll just write I will not use the set notation because set doesn't have ordering and this thing that we will learn tomorrow. This is in sequence, not a set. Okay, so for I getting a value in this sequence, first 1, then 2, then 3, then 4. Did I answer your question? Who asked the question? Did I answer it? Okay. Okay, so then you take the OR of these 2 columns. Okay, and the OR of the 2 columns, we know how to take the ORs of 2 propositions and we'll write it this way. It's clear? So if you're given a compound proposition, we know how to make truth table of it. It's not a very difficult thing, right? The other way around is a little tricky. Yes, please. See? You'll ask later? Okay, good. The other way is, and again we'll talk more about it, this thing. Suppose I give you a truth table and I want you to make a formula for it, a logical formula, a proposition for it, right? Why would we need something like this? Why would we need something like this? Yeah, get out of this problem and yes, please. Okay, why would you need something like this? Okay, so generally when you work in a tech industry, engineering, especially circuits, the businessman, the end user, they don't know formulas. They will come in, I want to make a circuit which should give me this output. The light should be on when I press this button and that button on and this switch off and that switch connected to that one and some. They will give you a truth table. This is the requirement specification of a digital circuit. Of course, very simple, but generally when you get a digital circuits request, you will get this thing. They will tell you when I give this command and not this command and I say this word and press this button and that stuff, I need this output. Okay, this is how what machine learning does this thing, right? So machine learning is learning from data. So some expert has given the correct output based on certain inputs, looking at the machine, looking at the patient's record. If this value is higher and this value is lower and this value is neutral and this value, this symptom exists, this symptom doesn't exist, mark it true. So this is a breast cancer positive. And if the other combination of values, breast cancer is negative. We record it like this and then we learn a logical formula. So we learn a computer program, that's called machine learning is, so there is a computer programming paradigm where you write a paradigm, input comes and output goes. AI or machine learning is in the inverse of that paradigm. Input and output comes and the input and old output came and the output of machine learning is actually a computer program. Okay, so that's the inverse thing and we'll talk about it some other time. So we get this type of thing and the idea is the thing is called functional approximation. I want to see what function actually produced this thing, what formula produced this thing, what was the expert thinking, what was the algorithm, the program used by the expert. right? So you approximate it. This is how we'll use it. There are two methods for this. We'll get more exercises for this thing in your problem sets. One is what I call the true rows method, and the other is the false rows method, right? If you really pronounce these true rows, what does it mean? So let me just give words to this two true rows in this particular case. We want a formula, whatever this formula is. It should be true when the input is either something like row 2 or it is like row 3. Yes? Is that the correct way to pronounce this table? This formula should be true when the input is like the second row, meaning when P is true and Q is false, or when the input is like the third row, when P is false and Q is true. Okay? So that's just a more concise way of saying what I just said. The formula should be true when P is true and Q is false. So I would just say when P is true and not Q is true, and or when not P is true, meaning P is false and Q is true, right? So either the first combination or the second combination should give me the formula. So my formula, whatever that is, should be either this combination should give a true on this combination or on this combination, or so I just put or, that's my formula. Okay? So if you learn how to pronounce stuff, right, how to just speak this thing, you will get the answer. Okay? The false row method is exactly the same thing. I want to make find a formula for this truth table. Is it the same truth table? I think it's the same truth table. So now this is what I call the false rows method. Okay, so obviously I copied pasted and I just didn't change. So this is called the false row methods. I just say this thing. This truth table tells me my formula should be false when the input looks like the first row, or and the input looks like the second row. Okay, because it's going to be exactly one of them. Yeah, whatever. Don't listen to what I say, okay? Listen to what I mean to say. When the input is the first row and when the input is the last row, my formula should be false, right? That's what. So if I say the formula is true when, okay, so the formula is false. So when the formula is true when these two doesn't happen, when the first row doesn't occur and the third row, whatever, the fourth row doesn't occur, right? You just pronounce the first row and the fourth row, you get yourself this formula. Okay, this is different than what we got last time, but nonetheless we got this thing. There are more exercises here. Do this. This is when somebody asked, or I just told you, this is the exclusive OR truth table. When you get a formula through the true rows method or the false row method, you will get a formula based on AND, NOT, and OR, right? That's why I said exclusive OR is a derived gate. Okay, it's not a fundamental gate, and then do this thing also. So this is one of the questions somebody asked that about implication, and somebody had some confusion is why does it make sense, or why should the truth table of the implication should be as it is. Let's just set up some terminology. When I say P implies Q, the P is called the premise of the statement or the condition of the statement, and the Q is called the conclusion or the consequence of the statement. Okay, P implies Q. The reason, the very fact that I give a different name to P and different than the name for Q, what does this sound? Huh? Okay, they are pulling the desk. Maybe it's upstairs. Desk. Okay. P implies Q. Just the fact that I give P a different name than Q, what does it mean? Huh? No, there are different propositions P and Q, but in terms of P implies Q, I gave P a name and Q another name, different name. What does it mean? Just basic common sense thing. What does it mean? Why didn't I give in P and Q, I didn't give P a different name than Q, right? In P, if P then Q, I give P a different name than Q. What does it mean?
There's a relation.
Yes, yes, there is.
One happens after the other.
Yes.
They're distinct.
Yeah, they're distinct for and also and or also. P is one proposition and Q is a different proposition. They are distinct, but why give them a name? The P, so in terms of A implies B, if I have a proposition, compound proposition A implies B, what will be its premise or hypothesis? The proposition A, right? What will be its consequence or the conclusion? The proposition B. So A is different than B. Why? So the basic, yes, please.
A to define B. You cannot define B properly without A.
No, absolutely no. B is a standalone proper proposition, right? We build upon it. We don't build B. We build upon B to make the compound proposition. Both A and B in that sense are equivalent. Yes. You want to say something? Yes. Didn't you raise your hand? Okay. Yes, please.
Both the same, then the value of the statement
No, the names are different. They're not the same. I'm not talking about their truth values being the same or different. I'm saying, why do I give them different name? Yes.
Sir, is it because the relation doesn't work the other way?
Yes, that's what it means. This is what it means. That means I cannot switch them, right? If in OR, if I have given this thing, that P or Q, let's call P the left guy and Q the right guy, then I won't be able to switch it, right? Then P or Q will be different than Q or P, right? It's not the case in OR and, it is the case with this. That's why now we distinguish between P implies Q and Q implies P. Okay? And that's what, so that's the first thing. Somebody asked this question, right now. Can we switch? You asked the question, right? That, so you got your answer. Again, if X is a general, X is an idiot. You change the order, becomes a totally different statement, right? If X is a law school guy, X is a subhuman or non-human. If you don't, you can't just replace it, right? You can't just say in the other way around. Yes? Okay. So that's the first thing, important thing you should note. Let's just talk about an if-then statement. If you solve the Goldbach conjecture, then you will get an A in the class, okay, in this course. That's a policy, right? I announce it. Let's go through the truth table. This is what we said, the truth table. P is a statement, you solve the Goldbach conjecture or you will solve the Goldbach conjecture. Don't go to the temporal logic yet, right? There's no time involved. You solve the Goldbach conjecture. Who is you? Whatever, you leave that. Q is the statement you got an A or you will get an A or you deserve an A or whatever, right? So that's Q, the statement you get an A in this course. Okay? Now, the truth table says, what is the first row in terms of, you substitute the value P and Q for the value for P and Q and pronounce the first row of this truth table. The first row of truth table says,
So you solve the Goldbach conjecture and therefore you got a name.
no, okay, so let me just say it this way. Let's suppose P is true, A and Q is true. That's the first row, the first part of the first row says that you solve the Goldbach conjecture and Q is true, you got an A, right? So P implies Q should be true, right? The value of P implies Q should be true. The policy is applied, nothing wrong, right? If somebody said this was the policy and this was the outcome, nobody is going to complain anything, right? No law school is going to involve, no court, no suit or anything. Okay? Now look at the second row. The second row is when P is true and Q is false. That's what people have confusion, and somebody asked that thing also. P is true, Q is false means you did solve the Goldbach conjecture, you did not get an A, right? P implies Q. Can I say that this is the class policy? this is what happened. You solved the Goldbach conjecture, you did not get an A. Can I say that my policy is, or my promise is true, that this statement here, if you solve the Goldbach conjecture? So the policy is violated, right? So the value of this statement should be false now. If you allow this type of things, then cannot be the policy. Okay, I'm going to give you many more examples, more relevant. That's just because we talked about the terminology again earlier. Also, Goldbach conjecture in A. Okay, the third row, in P is false and Q is true. This is also when people get confused. P is false and Q is true. What does it mean? What does it mean P is false? You did not solve the Goldbach conjecture, and Q is true, meaning you got an A, right? Anything wrong with the policy? Nothing wrong with the policy. You didn't solve the Goldbach conjecture, but you shined the instructor's shoes.
The statement being vacuously true.
Huh?
Would this count as the statement being vacuously true?
The statement being vacuously true, yes. The statement vacuously true or the statement obviously true. It's one of the two things. Vacuously and obviously have a meaning in the math literature. I don't know. The statement is vacuously true. Yes, I guess it's vacuously true. Or sometimes it says the trivially true, not obviously true. Trivially true or vacuously true. This is, I guess, vacuously true. Yes, please.
It also implies that perhaps there is some other policy in existence as well.
No, doesn't mean, yes, whatever. This policy is not violated. Of course, there are other mechanism to get an A. That's what it means. There are other means, other ways. When I ask you what's the difference between this and if and only if, the best answer I got was from the management sciences major, that it means there are other ways to get an A in this course, right? Yes, please. That's exactly the thing, right? The policy becomes angry when you meet the condition and plus the consequence, the promise is not fulfilled, right? Then it just doesn't make any sense. That then cannot be the policy, right? And this was also sometimes confusing when P is false and Q is false. Should P implies Q be true? So what P is false, Q is false means what? Quickly. P is false, Q is false. You didn't solve the Goldbach conjecture. You didn't get an A. Does it impact the value of the policy? It still might as well be a policy. It's a true statement. Okay, in this case, this may be vacuously true that he left. Okay, right? Remember this thing when I said it's a totally valid statement. If 1 is equal to 2, then I am the Pope. It's a totally true statement. Okay, if 1 is equal to true, that's false unless you believe in last lecture, or let's say from your previous knowledge this is false, right? Our current knowledge is 1 is equal to 2. Okay, but let's say from your previous wrong knowledge 1 is not equal to 2, 1 is equal to 2, 1 is not equal to 2, and I'm not the Pope, right? I'm not, but yet this is false and this is false, but this whole statement is true. If you make 1 equal to 2, then I will make myself a Pope, right? That's what this statement means. Is this clear? If you meet the condition, only then I am responsible to meet the consequence. If you don't meet the condition, then you can't. Is this clear? So this last row also people find confusing. Don't find it confusing, and if you do, think about it and keep thinking about it until the confusion is gone. Okay. There are a few methods that I will tell you off the camera sometimes. One good method that I found very interesting, and I always advise my students to do it. Anything that you find confusing, you write it on a piece of paper with your hands 20 times in blue pen and 20 times on black pen with black ink, right? With your hands, whatever concept you try and like. And then you write it on one piece of paper, and then you soak that piece of paper in water and drink it 3 times a day. Okay? Try it. You should try it, and it works. Okay? If that doesn't work, you did try it and it doesn't work, then I'll show you one more technique. It's very good, very useful. Not sanitized enough to say in front of a camera. Okay, so Okay, so the next one I want to show you some making other conditional statement from one conditional statement. So we have a conditional statement. One is called, and again somebody asked, and that's how we began this session, that why do we give them different names, the P and the Q, right? Because if you pronounce it in a different order, P implies Q, you write it, Q implies P. How do you say, what is Q, how do you say Q implies P? What does Q implies P mean? If Q, then P, right? It's a totally different statement. It's called the converse. Okay, the converse of P implies Q. And if you write it is not Q implies not P, it's called the contrapositive of the implication. Okay, and if you write not P implies not Q, it's called the inverse of the implication. Okay, you want one implication P implies Q. Converse means you make the consequence the premise and the premise the consequence. Contrapositive means the negation of the consequence implies the negation of the premise. The P implies Q premise. And the inverse means the negation of the premise implies the negation of the consequence. Okay. Let's see. So I'm going to finish this thing today, and it's not too many things left. You can see this these numbers. I go for a walk when the weather is sunny. Okay, let's just see how else can I say this statement. What does this mean, by the way? Just in plain Pashto, what does it mean? Urdu or whatever language you speak. Arabic. I speak a lot of languages, by the way. Arabic, Farsi, or Russian, English. What does it mean? What does it mean? If the weather is sunny, I go for a walk, okay? No? Okay. This is what it means. This is generally when I make a statement like this. If I go for a walk, then the weather must be sunny. Okay? It doesn't mean that as soon as I see the sun, I go out like crazy people, right? It only means when it rains, I don't go out. Do you see those statements? Okay? And I always think of this. Okay, so let's say P, I go for a walk. Q is the weather is sunny. P implies Q is this statement. If I go for a walk, then the weather is sunny. Okay? Remember, this only and if and these things are the if and only if, the by implication, that's if and only if and if the two generally one is the converse, one is this side. And the English, when you use the word only and where you use if in the middle, or it could be confusing. That's why think clearly, always write stuff if, at least initially, if P then Q. So it's clear what is the premise, what is the consequence. Yes, please. That's exactly what I did here. I wrote this statement, which was a little vague. Then I wrote it in terms of if and then, so that it becomes clear. Yes, please. Well, it's a statement is about me, so I know what I do, and that's why. No, but it's written here, I go for a walk only when the weather is sunny. I mean, again, the English is vague enough, but even if I want to say this thing, that I don't go for a walk. Okay, if you tell me, come to me, and it's raining, and you say, let's go for a walk. In my policies, I don't go for a walk in rain. What will I tell you? I'll just make exactly this statement, right? I go for a walk only when the weather is sunny. No? No, I don't say that. If you do, that's not what I want to say, and that's not what's written here. No? Okay. So, but that's not what I mean. I mean to say this thing. Okay, let's say this thing because I want to make a point to understand you this. I have made a statement if then statement. Okay, this was just for your practice to do a little bit of learn this thing that there is a curse of this language called English that you just can't say anything there. Everything can be misinterpreted and stuff. So you have to be careful with that, right? And so this is a statement I made. This is what I would write in terms of P and Q. If I go for a walk, then the weather must be sunny. Okay. Let's see what is the converse of it, the contrapositive of it, and the inverse of it, and see if they are actually the same statement or different statement, right? So that's the given statement. What would be the converse of it? What would be the converse of it? If the weather is sunny, then I go for a walk, right? I told you what I mean. My policy, my given truth fact is P implies Q. Is it the same as Q implies P? Q implies P means what? Every time the sun is out, I would be out. Right? That's not what I am saying here. The statement actually is saying when I would not be out. Right? When I will stay home. That's why I just told this. If in rain you come to me, let's go for a walk. I would tell you, I only go for a walk when it's rainy, it's sunny, right? So when I don't want to go outside, I will use this statement, right? So pay attention to this. What would be the inverse of it? So it's not the same statement as what's given, right? What would be the inverse of it? If I don't go for a walk, then it must be raining, right? Or it must be not sunny or cloudy or whatever, right? It must be the weather is not sunny. That's not true. Is that true? Is that what I said? Doesn't mean I don't go for a walk. If I don't go for a walk, maybe I'm dead. Right? Who cares the sun is there or is raining or whatever, right? Nobody said that. The statement said, if it's raining, I will not go out. That's what it says, right? Again, this is one of these examples that you have to listen to what someone means rather than what someone said, right? I never mentioned rain. I never mentioned staying inside, but the statement means that, right? When do you stay inside? That's what it wants. Okay, what would be the contrapositive of this? If the weather is not sunny, then I will not go for a walk. That sounds like what's P implies Q, right? What's actually I meant to say. Okay, here is a good example that you guys will understand. Please sit stably. I cannot go to these 3 slides later tomorrow, then you will miss it, and this is example where you will understand it actually. Calculus is the prerequisite of this course. Is that true? Okay, let's shoot if then. You took calculus, you took discrete math, you registered in discrete math, you passed calculus, whatever. There is a calculus course registration passing and there is a discrete math course registration passing. If then, what is this statement? Calculus is a prerequisite of this course. If you have taken calculus, you are registered in discrete math. Is that what is meant here? If you passed calculus, then you are registered in discrete math. Is that what is meant there? Right? Every single person in Punjab University has passed calculus. Even the law school idiots have passed calculus. That's not what is meant there. That means the other one. If you are in this course, then you must have taken calculus. Does it make sense? If you are taking discrete math now, then you must have passed or taken calculus some time ago, right? Is this clear? Never make this mistake. Okay? So that's the prerequisite word has a lot of context, right? The moment we translate it into if, then we make mistakes, right? Again, if you think of its converse and contrapositive and inverse, things will become quite clear. This is the converse of it. If you are taking discrete math, if you have taken calculus, then you must be taking discrete math. That's not true. Right? That's just not true, right? Law school student, calculus is supposedly a university core, right? Every guy has, all the ACF major have taken calculus, only 2 are here, right? That's not true. The inverse is if you're not taking discrete math, then you must not have taken calculus. That's not the policy. Prerequisite doesn't dictate that. There may be 1,000 other reasons why you are not taking discrete math. Not calculus is not a reason for this. Okay, this is another example that you should do. This will make perhaps more sense to you guys. And these are the truth tables of these things. And this one is the cool thing. You missed the best part of it.